Hello everyone, welcome to Signals, Systems, and Signal Processing with Wolfram U. The topic of this lesson is differential equation solution methods. After we mathematically model our system as a differential equation, we need to solve the differential equation in order to find the system response for an input signal x of t. In this lesson, we give an overview of how to solve those differential equations. We first consider the homogeneous part of the differential equation and solve the equation to get the homogeneous or the complementary solution. And then we consider the non-homogeneous equation and solve for the particular solution using a method called the method of undetermined coefficients. Once we have these two solutions, then we write the total solution as the sum of these two solutions. Let's go over each of these steps in more detail. For the differential equation, when the right-hand side of the equation is 0, we call the equation homogeneous equation. The solution to this equation is called homogeneous or the complementary solution, denoted by YCT. To find this solution, we simply consider the solution YT of the form e to the power st and substitute this solution into the homogeneous differential equation and get an equation that is of the form shown here. This is an algebraic equation that we can simplify first by factoring out the exponential term. And since e to the power st cannot be 0, the algebraic equation becomes this new equation. This equation is called the characteristic equation. And the n roots or the n solutions of these equations are called the characteristic roots of the equation. Once we have these solutions, we can write the complementary solution to our differential equation as a linear combination of n exponential terms as shown here, where the i's are the roots of the characteristic equation. This is the correct solution if the roots si's are distinct. In the case where we have repeated roots, the form of the complementary solution needs to be changed to avoid linear dependence. Let's say a root si has multiplicity k, then the solution will have the form shown here, where we have k terms corresponding to the repeated root si with the exponential part e to the power sit multiplied by t to the power 0, t to the power 1, all the way to t to the power k minus 1. And we can find these values of the coefficients ci's once we have the initial conditions for the differential equation. Since we have n coefficients to find, we need to have n initial conditions. For our first example, let's find a complementary solution to this first-order homogeneous differential equation. Using the Wolfram language, we can solve the equation. And if we plot this solution for, let's say, C1 equal to 0.5, we can see that the solution is a decaying exponential. This plot also shows the solution for more values of C1. You can see how the solution changes for different values of the initial condition. To find the solution by hand, we consider the solution y of t equal to e to the power st and substitute it into the differential equation to find the characteristic equation as we just mentioned. And factoring out e to the power st here, we get s plus 1 equal to 0 for the characteristic equation. The characteristic root will be minus 1, and so the complementary solution can be written as e to the power minus t. Let's now consider this equation. This is a second-order differential equation. Again, we want to find the complementary solution. We can solve this equation with the Wolfram language and find the solution. Assuming C1 and C2 are both equal to 1, this plot shows how the solution changes over time. We can also look at the plot for more values of C1. As you see, we have some oscillation in the beginning, and then the solution goes to 0. If we were to find this complementary solution by hand, we would consider the solution y of t equal to e to the power st and substitute it into the differential equation again. Simplify and get the characteristic equation as shown here. And then we find the characteristic roots S1 and S2. Now, since these roots are distinct, the solution will be a linear combination of these two exponential terms here. Next, let's consider the non-homogeneous differential equation shown here, where the right-hand side of the equation is non-zero. It is equal to x of t. To find a particular solution to this non-homogeneous equation, the particular solution denoted by ypt, we use the method of undetermined coefficients. The term that appears on the right-hand side is what we call the forcing function, or it will be a linear combination of several forcing functions. The method of undetermined coefficients can be used if these forcing functions on the right-hand side are of the form polynomials, exponentials, or trigonometric functions. If we have one of these terms, then we write the particular solution ypt in the same form with some undetermined coefficients. We then find the coefficients by plugging this particular solution into the differential equation and solving for the coefficients. Note that if any term in this solution, duplicates the terms of the complementary solution yct, then we multiply it by the lowest power of t that will eliminate this duplication. We will see how this is done in an example a bit later. Let's find the particular solution of this non-homogeneous differential equation. Since the input is a unit step function, it is a constant value, then using the method of undetermined coefficient, this forcing function falls under the category of polynomials, and so the particular solution must be a constant function. To find this constant value, we substitute ypt and its derivative into the differential equation and solve for the constant, which gives us c equal to 2. And therefore, the particular solution for t greater than or equal to 0 will be the constant value 2. As another example, consider this non-homogeneous differential equation where the non-homogeneous term or the forcing function is e to the power minus t. We want to again find the particular solution to this differential equation. The particular solution must be exponential according to the method of undetermined coefficients. But if you notice, this is also the complementary solution. So the complementary and the particular solution are not linearly independent. To fix this, we modify the suggested particular solution and we multiply it by t, as we mentioned earlier. Note that if t times e to the power minus t was also a term in the complementary solution, we would have multiplied by t to the power 2. The general rule would be to multiply the suggested solution by t to the power of the smallest exponent that would make this solution linearly independent from the complementary solution. We now substitute this solution into the differential equation and solve to find c. And so the particular solution will be t times e to the power minus t. Now that we know how to find a particular solution that would satisfy the non-homogeneous differential equation and the complementary solution to the homogeneous differential equation, we can write the total solution as the sum of the particular solution and the complementary solution. Let's look at one more example. Consider this differential equation with the given initial conditions y0 equal to 0 and y prime of 0 equal to 0. And let's find the solution yt. We can use the Wolfram language to find the total solution, and we can plot the solution to get an idea of what the solution looks like. But to solve for the solution by hand, if you remember, we already found the complementary solution, as shown here. Now the non-homogeneous term of the differential equation is 1 minus e to the power minus t times ut, which is a constant or a polynomial plus an exponential term. So the particular solution must also have the same form, constant plus exponential function. We now let the solution satisfy the differential equation by substituting it into the differential equation. And this gives us two new equations. If you look, coefficients of e to the power minus t on the left-hand side must be equal to 0, and c3 must be equal to 1, the constant value on the right-hand side. And so we now have the particular solution as shown here. And the total solution will be the sum of these two solutions. We still have these coefficients C1 and C2, and we can find their values using the initial condition. We have two equations for the two unknowns C1 and C2. Solving this system of equations, we get the value of C1 and C2. And the solution using these values will be given as shown here. We can also plot these solutions to see how they change over time. The complementary solution starts from some positive value. It goes to 0 after a while. The particular solution increases exponentially until it reaches 1. And the total solution is the sum of these two solutions. So in this lesson, we learned how to solve a differential equation that represents a system in order to find the system response to a particular input signal. We found a homogeneous solution, and we used the method of undetermined coefficients to find the particular solution. Then we wrote the total solution of the non-homogeneous differential equation as the sum of the complementary and the particular solution.